Hello. Uh, Thank you for being in my audience for this talk in somewhat unusual circumstances. This is a co-production between the machine learning team and Laboratory of Brain and Cognition, both at National Institute of Mental Health. The main motivation of our work was considering the notion of affordance, which is typically the properties of objects that determine action possibilities, and whether it could be extended to something beyond the typical focus on very specific motor actions like grabbing, pulling, etc., that are considered, without going as far as the extremely broad classical notion introduced by Gibson. And so in particular, we're trying to think what kinds of interactions, very broadly construed, are possible for each object that go beyond just the motor ones, whether similar objects support similar actions, and also how much of the mental representation of an object, if there is such a thing, is given to affordance versus other types of information. And the approach that we are following is to represent objects in an interpretable affordance space that's derived from text information, from text corpora containing instances of actions being applied to specific objects. So the paper is about how we can mine these and build an interpretable affordance space from them. There's a lot of related work, of course, namely on mechanical affordance perception. This tends to be more visual and motor focused, but also more broadly in affordance mining and selectional preferences in both NLP and computational linguistics. Our paper covers a lot of the key works, key related work in these areas. So if you're interested in it, I would refer you there. But let me tell you more specifically what we actually did. First, we created an object list, starting with pretty much every concrete noun in the 40,000 lemma paper by Brisbane, and then selecting nouns corresponding to picturable, non-navigable objects. So we try to avoid spaces. You're thinking more about concrete things. This is broadly construed, so it could be animals, objects, etc. And we expand each noun to all the senses in one net. This is then filtered by an object naming task, yielding a list with almost 2,000 objects. This has been the basis of a resource produced by our colleague Martin Hebert that pairs these lists of object concepts with lots of pictures, as well as various different kinds of norm data. So I encourage you to check it out because it's a really cool resource. For verbs, we built our own list by considering all verbs in all the categories in VerbNet, and then picking categories containing verbs that were deemed to correspond to actions performed by a human on an object. We only kept categories where all three human annotators agreed, and we didn't cherry pick verbs within a category. So if a category was in, every verb went in. We just eliminated some of the most common verbs, so on the order of tens of them, yielding a list with more than 2,500 verbs. Then we looked at a text corpus. In this case, it was a combination of UK WAC and Wikipedia, which between them have more than 100 million sentences. And we tried for every sentence in the corpus to produce a dependency parse, which gives you not just which words co-occur with each other, which is typically what's used in building embeddings, but specifically which verb was applied to each noun in that particular sentence. So in this case, we're interested in relationships where the noun is used as an object or as a passive object. And so we found all the sentences containing such things. And the result is a matrix containing all the counts of how often each combination of object I and verb J were found. Again, these entries reflect verb being applied to the noun, not just co-occurrence within the window. And this is important. So it's pretty sparse and much sparser than typical co-occurrence matrices. For those of you that do this kind of work, it was then converted to PPMI, and that's really what we are working with in the rest of this talk. So given the matrix, and in this case, I'm highlighting the row containing all the applications of verbs to object I, we factor that matrix as a product of first an object embedding matrix, which has a much smaller dimensionality for each object, 70, and I'll get in a second to why that number. And we multiply this by verb loadings over the verbs. The idea being that if verbs are applied to similar objects, then they're going to end up grouped together with high loading in one of these dimensions. Verbs might appear in more than one dimension, of course. And then you can approximate the row in that count matrix by a multiplication of the embedding for that particular object times all the loadings for all the dimensions. There's additional constraints on this that are picked to foster interpretability, namely positivity and sparsity. Positivity to say it's something that's either absent or there present to some extent, and different extents are comparable across dimensions. And sparse because we don't really want every object to have a particular dimension. That's kind of not informative. And conversely, we don't want one dimension to have every verb. Both of these things, sparsity and dimensionality, are determined via cross-validation using an interesting procedure that's in the appendix of our paper. And so after getting such an embedding, the first thing we're interested in is saying quantitatively, can we evaluate how much information it actually has about affordances? And for this, we turned to multiple affordance data sets. I'm only going to show you one here. This is in a paper by Arya Wang and Michael Tarr, where the subjects answered the question, what can you do with this object? And the top 5 verbs were collected. So this gives us answers for a pretty large number of objects and a fairly large number of verbs, which mostly overlap with ours. And so we can use this for a specific quantitative task where we predict for every object how applicable each one of the verbs in the possible answers are. And this is done by looking at their loadings on the verb ranking by combining those loadings using the embedding for the object. To evaluate this, we just look at the area under the curve for detecting the top 5 verbs. This is pretty pessimistic because it means that everything but the verb at the top will be slightly penalized by not being right at the top, but it's good enough to be used as a relative measure to compare this embedding with other alternatives. Namely, we have as baseline measures a variety of general word embeddings. So in this case, LSA, derived from our corpus, word2vec and glove, which are derived from much larger corpora. And for every object, we rank verbs by how similar their embedding vector is to the vector of the object. So quantitatively, we get, and this is on the left, we get areas under the curve on average that are quite a bit higher than those of general purpose embeddings. It's not entirely surprising because we are focused specifically on the question of which verbs apply to which objects. But on the other hand, this is behavioral data that was obtained completely separately from what we use to generate the embedding. The histograms just give you a sense of how the answers of where each value of AUC is present in each of the baselines is compared to the histogram for our method. So this tells us that there's information about affordances in our embedding, which is what we were hoping for. The second question, whether dimensions are interpretable, is a little bit more complicated because you can do it subjectively. I could show you the top 5 highest loading verbs in most of the dimensions, whatever I could fit in this slide to still have it be readable. And then I can try to interpret them. For instance, we can see that these are fairly broad motor actions that you do for many objects that are small enough to allow them. Then there are other actions that correspond more to certain types of modes of interaction with something, namely, for instance, an animal. And then are other things that are actions that are much more specific in terms of the category of thing that they apply to. So maybe screws, maybe lids. And for the second one, it might be something you do to fruits or vegetables. And then it can get even more specific. So verb 50 would be verbs that apply to things that have blades in them. 52 might be something that applies to limbs of some sort. So it's possible to do this, and we are in the process of running behavioral experiments to ask subjects to name the dimensions and give you a sense of what they correspond to. But we've came up with an alternative way of getting at this. Namely, we are going to use our dimensions to predict other dimensions that have already been validated with human subjects. These were done by us in collaboration with Martin Habert and published last year by analyzing a triplet experiment where subjects were asked to say which object is the odd one out. And given these three, you could get any of these three answers. They're all correct. But the key thing is they're all possible and they all influence the judgment. And over enough objects, you should be able to infer, as we were, dimensions that the objects have or don't have that explain the behavior in this task. So we take the objects, we produce a particular embedding, we compute similarities for every triplet between all pairs of objects in the triplet, and we use it to make a prediction of probability. This is done over 1.5 million triplets, and you get dimensions to represent them that turn out to be surprisingly interpretable. So each row contains the highest loading objects for a particular dimension, and the headings are the labels that we came up with. So far, so subjective, but I think you'll agree that these are not really weird dimension names to give dimensions. They make sense. But if you ask people, they will also give you names that are close to what we thought about. So it's possible to validate this. But now, given that we have these dimensions, we can ask the question, which of them are explainable as combinations of our dimensions? So over the same objects, embedding to embedding, can we predict each of the supposed dimensions with by combining our dimensions using positive weights, i.e. both embeddings are positive, they're being combined with positive weights. So such a regression model tells you that if it's possible to predict a supposed dimension, it is predictable by composing different aspects of meaning captured by the affordance dimensions. And to give you an idea what this looks like, for the dimension that was labeled as animal, in suppose, we are looking at the top 10 verbs and regression weights for the affordance dimensions that were most informative for this prediction. So you see for animal, one dimension, spot, observe, sight, etc., that corresponds to some things you might do with animals. Then the more aggressive verbs, another dimension that corresponds to verbs that have to do with exploiting the animal in some way. Another one for verbs of things that you might do to the animal, and others that have more to do with insects than mammals itself, indicating that, or rather, we know that the animal supposed dimension actually has insects as well. So it's more animate than animal. But you see that you can relate the two things. And in general, if you consider all the dimensions in suppose, and you can make a graph like this, where at the x-axis, we see the correlation of each individual supposed dimension with the best matching affordance one. Some are pretty close to being almost categorical in nature, but the interesting thing is if you look at the y-axis, where we show how well we can predict each supposed dimension from the affordance embedding, indicating that yes, generally you need several affordance dimensions combined to predict a particular supposed dimension, and the best predicted ones by far are the ones that are categorical in nature. After that come dimensions that are functional. They have to do with purpose, and some of these are classic categories or come close to classic categories. Others are things that definitely you can ascribe a name to, but would not be the typical lists that people use. After that, you have dimensions which are structural, and those are well explainable to the extent that they are kind of confounded with particular categories. And after this come, and these are less predictable, the appearance ones. So in conclusion, it is possible to derive an interpretable affordance embedding from text, and you can validate this both by predicting human affordance judgments and also the dimensions of suppose, which is a general model of object mental representations. The dimensions you can predict best tend to be categorical in nature. And the work we're doing now is trying to do behavioral experiments to validate this and try to learn more fine-grained dimensions. Thank you very much, and I'll take any questions now.